Yes, so I start the talk. So yes, classification of short-range entangled quantum states and pumping process, the joint work with Sven Bachmann and Martin Fraas, whom you probably know, and Alex Bols, my former PhD student, whom I hope you also know. He's currently at Caltech, and Tel Jappens is my present PhD student. Okay, and I have trouble, yeah, here. Okay, so we did not test it well. I have trouble going through the slides, but hopefully with some, yes, I think this is my first slide. Okay, so this is a little bit the setup. We are doing many body physics. I will have Hamiltonians. I was not sure what would be the audience, but so by Hamiltonians, I mean such thingies here, right? A sum of, for example, of sigma z's, which I write as z, and some sigma x's, acting on sides I and I plus 1, some nearest neighbor interaction. This is, of course, the famous transverse easing model, but I just want to say these are the kind of things that we'll be dealing with. For the moment, these are just large matrices acting on a Hilbert space with some local structure. So there is L spins, there's here spin 1, spin I, spin L. So if I write Zi, that means that's the sigma Z operator acting on spin 1, and this guy, the xi, is the x operator acting on spin I, so that would flip a spin in the Z basis. I think everybody is familiar with that. If not, then this might already be incomprehensible. Please stop me then. Okay, so another important notion, ground state vector. So if you have a Hamiltonian, you can look at an eigenvector corresponding to the lowest eigenvalue, since these are finite matrices that all is well defined. And we say there is a spectral gap if this E0, the minimum of the spectrum, is simple and it's separated from the rest of the spectrum by some gap that is uniform. And mostly when you hear thoughts that start like this, the goal, the big overarching goal is to study gapped ground states, to characterize them, classify them, and perhaps study their exotic low-line excitations as anyons or fractons recently, and to get a theory of that. Of course, I guess my talk fits in that program, but of course I will be doing something rather specific. So here is how I want to start. I want to give you a small result that I think most of you are in some form familiar with it. That's why I want to start with it. So this is the Thouless pump. And what is a Thouless pump? Trying to get this taskbar out of the way. I don't know whether this, it's a bit annoying, but okay. So a Thouless pump, for that you need some Hamiltonian with a gap ground state psi. You need a U1 chart, U, which in this setting it could be simply the sum of the Z magnetization, so the sum of sigma Z's, and this U1 charge has to be conserved, otherwise it does not help us much, so it commutes with the Hamiltonian. And then I will consider some unitary that will implement the pump, that I will not sketch too much in detail now, but that would, for example, well, certainly needs to satisfy that it leaves this state, so this ground state invariant. It needs to commute with the charge, so it needs to leave the charge invariant, it conserves charge, and it has to preserve some locality. So for example, if you let this unitary transformation act on something supported on side I, then you can perhaps get something that is again on inside I and has a bit of spread out to sides I minus 1 and I plus 1, but those have to be small, and then there is a bit of spread out even further, but that has to be even smaller. Actually, I don't mean this literally, right? It's not that it has to become small immediately. Perhaps it can have a contribution of order 1 living in a ball of radius 10 around side I, but at some point it has to decay. That's what I mean, that U preserves locality. That's sort of some natural, I mean, it's a natural object in many body physics. And then if you now look what this transformation or pump U does to the charge in a certain region gamma. So the total charge is left invariant, but the charge in a region gamma, of course, is not necessarily left invariant. However, in the bulk of the region gamma, nothing happens, because there you actually don't see that you are not considering the full charge, but only that in a region gamma. But at the boundaries of the region gamma, you see that something is happening. And to make that precise, you can write the transformed charge in gamma minus the original charge in gamma as a sum of two contributions living at the boundaries of that region. So T minus lives here and T plus lives here. Right, is supported there. Okay. Now, by the fact that the state was assumed to be invariant under U, you can convince yourself that the expectation values of these two transport operators, T minus and T plus, the expectation value of them together is 0. But, and this is the point, and now I really have to move the taskbar. The expectation value of either one of them is not necessarily 0, and actually the famous thing about the Thouless pump is that this expectation value of this transport operator, which is something like the transported charge across that boundary, is an integer up to errors that decay faster than any inverse polynomial as the volume L goes to infinity and the size of this region gamma goes to infinity. So that's sort of, if that's the first time you hear about that, it might seem a bit trivial, because after all, charge is something quantized itself, right? I mean, this operator here has integer eigenvalues. So you might say, okay, so whenever you find charge, you find 3 quanta of charge or 17 quanta of charge, but never 3.5. But that does not quite explain this result, because you see here there is an average over something in a state, and moreover that something is not longer the charge in a full region or in some sub-region, and it's a priori not so trivial that this here also is actually quantized and is an integer, but it's true. Okay, so this I hope that in some form you have seen this. I did not give reference here because there is a lot of people who worked on that and who proved versions of that. Of course, the one I put here is something that we proved a few years ago. So this goes by the name quantization of charge transport in a Thouless pump. And this is really a motivation for what I will be talking about now. So I want to understand this setup better. And I want to ask a question which probably you did not see asked when you met Thouless pumps, namely whether this transported charge in some sense fully classifies the pumps. And that will be true. And then it's also natural to ask, well, perhaps does it classify also the states itself that it acts on? That might seem a silly question. Sometimes the answer is just yes. It will be a natural question in the form of in the course of my talk. And then also up to now, this Hamiltonian was playing a prominent role, and the state that I consider was defined as a ground state of it. And actually this was technically also important because it guaranteed that the ground state had good properties, like an area law or decay of correlation. But somehow we want to think whether this Hamiltonian actually is really important for the story, or whether it's just nicely behaving states that play a big role in the story. And then finally, this is not as important as it might seem. I actually want to get away from this U1 charge and have a general on-site compact symmetry group G, because sort of such things are considered often, right? You might seem that the U1 charge is very fundamental, and I guess it is, but models of condensed matter very often have some more emergent symmetries, and so it's certainly natural to study these models. Okay. Good. So for these new questions, and I need a little bit more technical setup. In particular, we'll move now to infinite volume. But I think for the people in the audience that I know, they are very well familiar with that. So there will now be, instead of just a Hilbert space, there will be a spin chain algebra. It's a quasi-local C-star algebra that you can think of as, well, it's actually a subset of this infinite tensor product, but of course with the right norm. And on each side, I now just have an on-site algebra which is a finite matrix algebra, which previously I suggested it's just qubits, so then n would be 2, but I actually will need more general situation. So just a matrix algebra on each side. Hamiltonians, strictly speaking, will not longer be well defined as elements in the algebra, but they can be interpreted as derivations on the algebra. So I will never really need the Hamiltonian. I will actually need the commutator of the Hamiltonian with something in the algebra. So that's a derivation acting on the algebra, and that can be defined as the sum, where HS are now just local operators, so they are elements in the algebra. And when I write HS, that means that there is an operator self-adjoint acting. Oh, that's not good. There must be a way of doing this better, this scrolling, but I don't see it, so that's why I'm yeah. The more I get agitated, of course, the more mistakes I will make in scrolling. So good. Yes, so HS acting on spins in S. Now, of course, you cannot have any term here. They must have some sort of locality. So as S becomes bigger, the terms that sit here must become smaller, and we will always in the background have some norm that makes that happen. So here I put the norm of HS, but I divide that by a function basically of the diameter of S, and that function has to grow faster than any power. And then sort of that thing here has a chance to actually be finite if those the norm of these terms decays fast enough, and that will be the meaning of such norms. Okay, I will not really mention them anymore, but whenever I say Hamiltonian, you should think that it's constrained by having a finite F norm in this sense for some F. That's a natural class of Hamiltonians to talk about. Okay, then these Hamiltonians will actually will serve to generate automorphisms. They will, in my talk, in contrast to the first slide, they will not be a fixed Hamiltonians. They will be time-dependent Hamiltonians indexed by a time going from 0 to 1, and that will generate some automorphisms in the way that I actually did not write it here, but you know how a time-dependent Hamiltonian generates an automorphism of the algebra at time evolution. Okay. I guess that's all on this slide. So if somebody knows what I should do to just be able to click, please tell me. Yeah? I never encountered this problem before in a Zoom talk. So the last slide of the technical settings, we need a G group, a group G of symmetries acting on site. So this is just a family of automorphisms acting on the matrix algebras, and this extends to the full algebra. And just to, if you are a bit lost by this, previously when I was just having U1 charge, then these automorphisms were of course on site, just conjugating by this Zi operator, and where you recognize the generator of the charge, but on a given site. So I think this is all pretty standard. Then we will have states. Instead of vectors in a Hilbert state, we'll have normalized positive linear functionals of the algebra, and we will actually only consider pure states. Those are states that cannot be decomposed into two other states. And often we will assume these states to be G invariant, meaning, of course, that applying first this automorphism for a certain group element G, and then the state is the same as applying the state. I will not always say when a state explicitly that I want the state to be G invariant. I will just put somewhere a prefix G, and I hope it will be pretty clear when states are assumed to be G invariant and when not. So the going to this infinite volume limit is not really essential, but it makes proofs and statements a bit shorter and neater. So I thought we would go with it, and also the paper is written like that. Okay, so here is a first concept that you might actually not know, short-range entangled states. So a short-range entangled state on a spin chain, it can also be in higher volume, but I mostly be dealing with chains. A short-range entangled state means that there is a time-dependent Hamiltonian generating an automorphism such that the state psi is reached by that automorphism starting from a product state. right? So you have a product state, you apply the automorphism, which is a time evolution, and then you get the state psi. Okay, so for gapped ground states, if psi is a gapped ground state, being SRE basically means, or not basically, this can be made into a theorem, means that the Hamiltonian of which psi is the ground state can be smoothly deformed into a trivial Hamiltonian of which P is the ground state, and this can be done without closing the gap. Okay, so it's a bit unfortunate that I used here H and here H as well, because this H here has actually nothing to do with the Hamiltonian of which the state might be a ground state. This H just generates the adiabatic evolution, taking the state to the product and taking implied by the deformation of the static Hamiltonian from being the Hamiltonian of which psi is the ground state to the Hamiltonian of which P is the ground state. So I see that I messed it up by having here 2 times the same letter. So anyhow, if you did not get that, it's not important for the rest of the talk. So then let's see, where do we find SRE states? Well, let's look at our favorite model, the one-dimensional transverse Ising model that I had already. If you have ever looked at this model, you know that it has a quantum phase transition in the ground state. There is a critical value of G. Below this value, there is symmetry breaking. You have basically all ups, dressed versions of all ups, all spins up, and dressed versions of all spins down, which are the ground state of that. And those states would both be SRE because you can there deform this Hamiltonian so as to eliminate the second term, and then you will basically have a trivial Hamiltonian. Well, you will have basically just the Hamiltonian without a G, but then the 2 ground states of that, all spin up or all spins down, are also ground states of just Z on single sides, right? But then you have to choose plus or minus, indicating whether you have the all up state or the all down state. And on the other side of the transition, you can also smoothly deform so as to eliminate the first term, and then you will be left with sum of sigma x, and that's of course also the ground states of that are of course also product states. So so on both sides of the transition, we can actually prove here that the ground states are SRE states. At the critical points, you have a critical state which is not SRE. For example, because it does not have decay of correlations, or it does not have exponential decay of correlations, which already prohibits it of being an SRE state. Or better said, it does not have faster than any power law decay of correlations. In my definition of SRE states, I allow that they don't have exponential decay of correlations, but the correlations have to decay as any power law, faster than any power law that was dictated by my condition on these Hamiltonians H. In any case, this guy here sitting at the critical point is not SRE because it's correlations decay algebraically. Okay. You don't need a gap to have an SRE state. 3D ferromagnet with spontaneously broken SO3 might be an SRE state. I mean, in the simplest examples, it's actually a product state, so it's certainly an SRE state. On the other hand, having a gap does not mean that you are SRE, and there the normal examples would be, or the most known examples would be fractional quantum Hall effect with anyons. These are states that have a gap, but they certainly have long range entanglement. They are not SRE. Okay. So this outlines a little bit what is the scope of these SRE states. This is a side remark. There is a natural conjecture about SRE states. First, let's start with the facts. Every one-dimensional SRE state can be realized as a gap ground state of a nice Hamiltonian. That's very easy to see. I will not go through that, however. And then there is a folk wisdom, I say here, and that is that in one dimension, the converse is true. Every gap ground state is SRE. And most people, if you find a random passerby and you will ask him this, he will say, of course, this is true that it just expresses that there is no intrinsic topological order in one dimension. There are no anyons or funny business like that. It's well known. And it's true, it's well known, but actually, and I don't know whether, well, I'm convinced it's true, but it seems to me that there is no proof. There are proofs of a lot of things about one-dimensional gap ground states, decay of correlations, area law of entanglement, split property. I will not explain that, but for those who know what that is, all these properties push a little bit towards convincing you that there should just be SRE. I started trying to prove that actually, as I realized there is no proof a few months ago, and there is still no proof. I still think it must be easy, but yeah, we still have no proof. I think it's a very nice problem to work on. Okay, so let's now try to bring some structure into this set of SRE states, and we'll define an equivalence relation on them, which will be a little bit trivial. The equivalent relation between two SRE states just means that you convince them that you can connect them again by some time-dependent Hamiltonian, right? And then we'll immediately refine that notion a bit. We're saying, well, sometimes you might not be able to connect them, for example, because they live on spin chains where the on-site dimension is different. But then we allow to adjoin or stack, as it is called, product states to your system, and perhaps then you can connect them. So this stacking operation here, where you add a product state, is a little bit, should be thought like that. So you have a state here on a spin chain, here some other state on a spin chain with perhaps different on-site dimensions, and now you just put them together, which means that you put the sides together side by side, right? So if that was a product state and that was a product state, then I now have a product state on a chain where the on-site spaces are bigger, right? The on-site matrix algebra is a product of the respective on-site algebras. That's called stacking. It works also for non-product states, of course. That's called stacking, and that's what is meant here by this tensor product. Psi tensor product with P means I stack a product state. And it's, as you might have noticed already, it's necessary because, well, I said it already, otherwise systems with different on-site dimensions are never equivalent. On the other hand, you could be worried that now this equivalence relation is actually a little bit trivial. After all, I defined SRE states by the fact that they are connected in more or less in this way, not more or less, in this way to a product state. And now I'm saying two SRE states are equivalent if they are also connected in this way, but that upon using the stacking operation, you will quickly convince yourself that actually all SRE states are equivalent. So that cannot be a very interesting notion that I defined here. And it is not very interesting. We'll add an ingredient to that. And the ingredient that is added to that is G invariance. So now I do just the same what I did. I have SRE states that are now G SRE states, so they have to be invariant under this G group G. And when I say that they are equivalent to each other, that all has to be within the set of G invariant SRE states. And now this notion becomes non-trivial. Now it is possible, and actually it does happen for some groups G, that the set of SRE states, which was a connected set under this equivalence relation, now becomes disconnected and breaks apart in components. And actually, I think you probably heard even some talk about that, because by now this is a very well-known problem. It took more or less 10 years between, I would say, between the first realization that these connected components are classified by the second cohomology group of the G, and the final mathematical results of that, which really made that completely precise. The result by Yoshiko Ogata and then Kapustin, Sopenko-Yang in the same year. I think these are very satisfactory result that made it completely precise. So just to say, when I say that a set of SRE states is classified by this group here, right? The second cohomology group of a group in particular is a group, then I should say, what is then the group operation on this SRE states? And the group operation is stacking. Stacking modulo this stable operation. So modulo the equivalence relation and stacking modulo the stable equivalence relation. That's the group structure that I will put on these SRE states. And if you do that, well, then you see that the set of SRE states is group homeomorphic to this second cohomology group. Of course, you are not expected to understand that just because I stated it. I just wanted to state it because it's a famous result and it sort of shows that the set of SRE states can have an interesting structure. Okay. I also want to connect this to something that you must have heard in other talks on topological insulators, where there are very similar pictures, right? You have these toruses, which are not quite the same as a ball. And if you want to deform into the same, something catastrophic must happen. And physics-wise, this catastrophic thing is then translated to a gap closure and so on. And that's a little bit the same game as is playing here, except that here we have abstracted out the Hamiltonian, so we don't really have the gap anymore. Right. So, but if you now reinstate the Hamiltonians again, you think that these SRE states are ground states of a Hamiltonian, then actually you would have a gap closure at the red lines here when you go from one phase to the other phase. Right. So there you have no SRE states available because the corresponding ground state would be gapped. Okay, so you could now actually ask, is it perhaps the same problem as the one that you heard about in topological insulator talks? Well, it's not really the same problem because those classifications usually deal with non-interacting systems. We deal with interacting systems. Actually, we deal with spin, so it's not even very clear what non-interacting system would be, except in free spins, which is not very interesting. So there is not really a one-to-one correspondence, right? Some problems here on topological insulators translate into a very similar problem in my sense, but some interesting classes here do not have an interacting counterpart, and vice versa. Some in nice interacting phases do not have a non-interacting counterpart. It's really a similar but different problem. Okay, so now unfortunately I need still one more notion before I come to some conjectures and results. I already said what is an SRE state, but now I will have a slightly weaker notion of invertible states. And a state is invertible, and I think the notion is due to Titayev, as most of the things in this field. A state is invertible if it has an inverse, such that when you stack it with its inverse, it becomes SRE. So obviously, by nature, this invertibility is a weaker property than being stably SRE. In one dimension, it's actually equivalent, as was shown by these guys. And it's really, in higher dimension, it is really richer because it is known, between quotation marks, that, that states which have an integer quantum Hall effect are examples of invertible states in 2D that are not stably SRE. Right? So, to be honest, I don't know a proof, even not of this fact, even not that they are not stably SRE. So, but I think it must be possible to make a proof. Anyhow, all clever people seem to be convinced of that, so I guess it is true. Right? So I repeat, what is the point? So invertible states are almost SRE in the sense of what I write here, but they are not quite SRE, and the most well-known examples are states with carrying an integer quantum Hall effect. Okay, of course, more exotic states like states with of the fractional quantum Hall effect, states of anion excitations, are not invertible. So there are still a lot of non-invertible states. Good. Now I think I'm ready to state some conjecture. Well, I still need my pumps, right? So that are the invertible states. Those are the class of states that I will consider. And now I will pump them, and pumping them here will actually mean that I consider loops of these states. So a loop, a path, closed path of G invertible states, right? Parameterized by a time s, and psi0 is equal to psi1. That just means that it's a loop, okay? Now, actually, I misled you a bit because you cannot yet completely know what I mean by a loop of states, because I did not yet tell you what I do to constrain these loops to be continuous. Actually, there, as far as I know, and sort of other people think likewise, there is not really a good topology to say that a loop is just a continuous closed path. So we don't talk about topology, but we say explicitly what it means to be a good path, and that, as you could have imagined from what came before, just means that this path is generated by a time-dependent Hamiltonian. So that's what I mean by loop, right? So states parameterized by time, generated by some nice time-dependent Hamiltonian. And that really replaces the notion of continuity. Okay, and then what are equivalent paths? Because I want to classify pumps, so I have to say what are equivalent pumps. So I have to say what are equivalent loops, and I will here I will do that. So when is a path here going upwards, a function of s equivalent to another path? Well, if you can go in the other direction, so in the lambda direction, also if that is also generated by a time-dependent Hamiltonian. So I have actually a sheet of states, a two-dimensional sheet of states, and transport on this sheet in s direction is generated by this vector field implemented by some time-dependent Hamiltonian. And in the other direction, it's also implemented by a vector field generated by a time-dependent Hamiltonian. So it's a little bit abstract, but it's a natural notion since we don't have any good notion of topology. So the good thing that we can do is that at least continuity in s direction and continuity in lambda direction sort of are defined in the same way, namely being generated by a local Hamiltonian. Okay, so I said what are loops for me. I said when two loops are equivalent, hence homotopic. And now perhaps I can get to some real stuff. Yeah, the real stuff here is a conjecture, of course, by Titayev, and the conjecture goes as follows. So if psi is a G invertible state on ZD, and you make loops, G loops, starting at that state, so with base point psi, then these G loops will be classified by G invertible states of one dimension lower. That's the conjecture. Let's see what this conjecture would mean for D equal one dimension, where I'm mostly interested. So then we need to see what are G invertible states in 0 dimensions. Luckily, in 0 dimensions, all this SRE business or invertibility becomes empty. It's very easy. And we just need to classify G invariant states in 0 dimensions. So basically, that boils down to classifying the vectors in a Hilbert space, and you have a unitary action of G acting on these vectors and leaving that vector invariant, which means that, well, it does not have to leave the vector invariant, it has to leave the state invariant. So you can have a phase multiplying that vector phase depending on the group element G. And you see that this assignment of G to the phase is a scalar representation of G, scalar representation of G. So something in the home set of G to S1. And so now we can, that set here, that home set is then the natural classifying space for 0 dimensional states. That might sound a little bit abstract, so let's just give an example. In the case that we understand where we have a U1 chart, so then we need to consider U1 states, states invariant under the U1 action, and they are indeed characterized by a Z charge. Why? Because the scalar representations of U1, well, that's just a winding number. They are characterized by a winding number, so indeed Z. So it works out for the one example that we are familiar with. Right, I repeat, so G invariant states in 0 dimension are classified by this Hom set. Okay. So what is now the result that we can prove? Well, the result that we can prove is basically that we prove this conjecture for the case D equal 1. So that's here. So there is not more to that. We just prove that conjecture, but I sort of unpack it a little bit to remind you what this actually means and to be a bit more concrete. So we actually construct an index of loops of one-dimensional G invertible states, such that if the loop is constant, then the index is 0. For any H in the Hom set and any base point, there is a loop with that base point such that its index is H. If two loops are homotopic, then their indices are the same. Conversely, if two loops have stably equivalent base points and they have the same index, then they are stably homotopic. Stably homotopic is a natural generalization of this notion of homotopy. Again, you are allowed to stack some product states. So that works nicely out. And then there are, of course, some obvious additivities. If you stack two loops, then their index is the sum of the indices. And also if you concatenate two loops, you do one after the other, then the index is the sum of the indices. Okay, and most importantly, because we lost that a bit out of sight, that index also has a nice interpretation as the pumped G charge. I started my talk by talking about pumps. Those were U1 pumps. And so I hope now that, well, it's true, but you might hope now that this index that has been constructed here in a rather abstract way, or at least presented in an abstract way, indeed measures something like the transported charge, at least for the case of U1 pumps. And it will be so. Okay, so let me now explain you that and explain you what is being pumped and how this index is constructed. So here I just go back to the U1 pump, right? So pumping charge, the sort of charge that we know very well. So you can look at that as having a reservoir on the left and the reservoir on the right, and what goes out from the reservoir on the left has to be added to the reservoir on the right. That's a very pleasant definition of pumping, but this definition is no longer very appropriate if your charge is not in Z, but rather in something like Z subscript 2, right? If the charge takes values plus and minus 1, then you cannot really accumulate it, right? You add 7 times charge 1 and you still have charge 1. So so we need something better, right? We need another way of looking at this pumping process, and here is another way of looking at this pumping process, and that is you truncate the Hamiltonian in the middle of your system. So it acts only on the left, and then you switch on the pump. So you do the time dependent. You look at the evolution generated by this truncated time dependent Hamiltonian, and now of course your loop is no longer closed. Your pump did not go back to the base point because you mutilated the Hamiltonian. So we have now what we call a pumped state. Right? In particular, I will use this pumped state at s equal to 1 at the end point of the loop. And as I said already here, this pumped state is not the same as the base point because I mutilated the Hamiltonian. However, to the left of this cut, the pumped state does not really feel that you mutilated the Hamiltonian. So there it is equal to the base point after completing the loop. And on the right, well, the Hamiltonian was mutilated very much because it is completely set to 0 now, but that's also good because that means that there the state actually never moved, right? So after completing the loop, you are still at the base point where you actually expect it to be. So the point is that far away to the left and far away to the right, the pumped state is equal or is similar to the base point. That is intuitively so, but it is also true in the sense of states on a C-star algebra, and there is a notion for that. These states are equal at infinity, what that just means is that this pumped state can be fitted into the GNS representation of this state, right? That now went a little bit fast, but I think it's, well, I'm not really giving the proof. I think it's intuitive. What I really wanted to say is that the pumped state differs from the base point basically in a finite region. And therefore, it has a chance to be in the GNS space of the base point. And that is actually the case. So the pumped state, which I will now abbreviate as this, has a vector representative in the GNS space of the base point. And this actually makes the study of this pumped state into a zero-dimensional problem, because we actually have now just bona fide states on a Hilbert space and everything is pleasant and nice. This GNS space inherits a unitary representation of the group action. And so we can now play the game that I already outlined for defining the zero-dimensional index. Right? You can just look how this unitary acts on the pumped state. The pumped state is actually G invariant because it's, I mean, the truncation of this Hamiltonian could have been done very easily in a G invariant way. And so then you did not break the G invariance at any point. So the pumped state is G invariant. So this guy has to act on it in a scalar way. It acts on it by multiplication with the phase. And that defines, again, this scalar representation H. And this scalar representation H is, well, in this home set. And that was my index of zero-dimensional states. So what did I do? By truncating the Hamiltonian and looking at the pumped state, I basically got for free something that is in this home set, and that something indexes zero-dimensional states, G invariant states. So basically, I got what I wanted, right? At least, well, I did it sort of. I stressed a bit the U1 situation, so perhaps the way I told it does not really make clear that it's valid also in general, but it is valid in general. Okay, where do we go from here? Okay, so that let's now give some examples to see that actually there's really that there are examples, there are non-trivial examples. So they are constructed a little bit in an artificial way. Since I know that that I want this home set, I will actually pick examples where the on-site Hilbert space is spanned by vectors which are basically labeling elements in the home set, right? So another way to say that is that I have, it will be enough to have three vectors for, I target a given element of the home set, and then I just need the three vectors, the zero element of the home set at the H, and then the minus H. Yeah, now I have to get back. Yes. And another way of saying all this is that I fix the group action so that indeed for each of the three choices here, indeed the state transforms by this unitary action as with the given scalar representation. So that indeed the zero-dimensional index of this zero state is zero, and the zero-dimensional index of this H state is H. Okay, so it's all basically a tautology. Okay, and now I'm ready to do some action, and the action I will do is I will group the sides in groups of two, and on these two sides I will do a transformation. I start with the zero state everywhere. It's a product state, and I change this 0, 0 into minus H, H. You can convince yourself that on these two sides taken together, you have the same zero-dimensional index. So this is a process that can be done without breaking G invariance. So it's a possible process. I think it's also, I mean, it's also self-explanatory almost, okay? And I do that on each pair of sides. So I have here minus H, H, minus H, H. And then I go back to the 0, 0 state, but by contracting not this minus h with that h, but that h with this minus h. And so that works. I go back to the 0, 0 state. And now I truncate the Hamiltonian here, which means that here everything stays the same, but here nothing happens. And then when you go back to the 0 state by contracting in a shifted way, you see that this guy is happy because he finds a partner here, but this guy does not find a partner here, and so he will not go back to the 0 state. So actually, by G invariance, it's not the only thing, but one thing that this thing can go to is H0. It could also go to 0H, but that would not matter. In any case, the index of this state, right? The 0-dimensional index of this state, in some sense, in the GNS space of this state is just H. So this is an example of a pump which pumps charge H. Okay, and basically you can make an example like that for anything you want, and that's and then the theorem that we had was in some sense saying that these are the only possibilities, that all other pumps are stably homotopic to such things. Okay. Now let's see whether so the rest I still have some things to say, but perhaps I don't know. Can I still continue a few minutes, or should I stop?
Yes, you can.
Okay. So then I think I choose to not. So there is something non-trivial about my proof, or our proof. Yeah, it's really our proof. It's not that I did this work alone. But I prefer to tell you the problem in going to higher dimension. So as I said, the Kitaev conjecture is valid in higher dimension, or it is a conjecture in higher dimension. I think the statement is probably true, and I just would like to meditate with you a little bit about what the problems there are. So you can do the same thing in higher dimension. So let's do 2 dimensions, and let's say that we truncate now the Hamiltonian to the left. Unfortunately, on this picture, I truncated it to the right, but it does not matter. So you do this. So you have your time-dependent Hamiltonian, you truncate it to the right, and you do a loop, right? And for the same reason as before, the state that you get, the pumped state here, psi minus, right, is actually similar to the original state. And I forgot to say the original state here is a product. I start the pumping process from a product. So the pumped state is similar to the product on the left, of course, because there actually nothing happened. That I did not do any pumping protocol, I just had Hamiltonian 0, and it's also similar far away from this line to the right. Why? Because far away from the line, you don't know that there was actually a truncation of the Hamiltonian at that line. So far away from this red line, you are similar to the base point. Okay, so actually, if in some, we don't really have a GNS representation here, but this is actually not really a problem. The point is that relative to the product state that we started from, we have all the information that we have now is contained in a quasi one-dimensional state. What do I mean by a quasi one-dimensional state? Well, a state, as I already said, that goes to this product far away from this line. But unfortunately, you cannot say starting from distance 10 from the line, it is exactly the product state. Of course, there is no reason why that would be true. However, this is really the thing that blocks us, because, oh, not yet. Yes. We actually want to prove that these pumping protocols are classified by one-dimensional invertible states. I did not speak yet about the invertibility of that state, but that is not the problem. My quasi one-dimensional state is invertible. That can be checked easily. That's easy algebra. But the point is, I am nothing with the quasi one-dimensional invertible states unless I knew that the classification of quasi one-dimensional invertible states is the same as the classification of one-dimensional invertible states. So in some sense, what I need to do, what I would like to prove, is that this quasi one-dimensional state here can be by this by the equivalence relation that I have, so by some time evolution with the local Hamiltonian, that this guy can actually be mapped into something which is sharply cut off, so which is just living around this vertical line, and then to the right of this strip, it is exactly the product state that we needed, right? So I sort of need to fit this quasi one-dimensional state into a finite strip. If I would succeed in doing that, I think we would have a working proof of this Kitaev conjecture. Now, it seems like a silly problem, but I'm stressing it so much because I actually like this problem a lot, that to fit this quasi one-dimensional invertible state into a finite strip. If it were just about SRE states, it would be trivial. I would know how to do it. But because of it's an invertible state, I actually don't know how to do it, and I like this problem. Okay, perhaps that's not so clear why you should like it, but I think it's a very natural problem because you see people are classifying these states, but sort of if it would not be true that quasi one-dimensional states are actually the same as for the classification as one-dimensional states, well then this classification of one-dimensional states would also not be such a natural endeavor. So I think it is an important question, and it's also important for us because then we can finish our proof. Okay, good. So I think it's not a good idea to go back to the missing slide because I think it's better to leave more time for questions. So thanks for your attention.
Yeah, thank you very much, Wojciech, for this very nice talk. And we can now have a discussion. Are there questions? Let me start with a basic question. You gave us a general framework for the SRE states. The examples you gave were mainly spin systems, but that really doesn't depend on that. If you had something else like fermion or boson algebras, would this be similar? Are there any examples that we can treat?
So certainly the definitions would apply, and these are relevant definitions. The results are not necessarily exactly the same. So, for example, something that when I have not worked on it for long, I always forget. But something that is also called the Kitaev chain. You know the thing with the dangling Majoranas at the ends. You know what I'm talking about, right? So that is an SRE state which is not protected by any symmetry and which still is a non-trivial. That would, in my framework, not be possible, but in that framework, yes, because of the fermionic nature. So I'm just saying the definitions are true, but the results are a little bit different, need to be changed a little bit.
Mm-hmm. Okay. Is there any, maybe it's also not so easy to state, the SRE states, I'm trying to understand them also in terms of maybe entanglement entropies. Can you classify them in that way as well?
Oh, I guess that's a good question. Yeah. So so let's go to something. Yeah. So this is well. It's certainly true that if you have these eggs here, right? These disconnected component, there is one that is trivial, and that can be mapped into something which is a product. So that has then zero entanglement entropy. But of course, the original state, the entanglement entropy could have been, they always have an area law, but the entanglement entropy could be 100 or so, right? But then if it's trivial, then you can map it by this adiabatic evolution to something with entanglement entropy 0, whereas for the other phases that's not possible, right? You can never map it to something with 0 entanglement entropy because you need still a little bit of entanglement there. But if you just look without this adiabatic evolution at the entanglement entropy of the states itself, no, then it's not helping you to classify that because it just might be large.
Yeah.
Another way to say it, entanglement entropy is not an invariant of this equivalence relation that I had.
Mm-hmm.
Right? It's changed by adiabatic evolution.
So could you refine it so that it's
Did you still say something or?
Yeah, so my question was, could you refine it somehow so that it could distinguish?
No, I think, well, it's not the game that one is playing here. You see, well, I mean, the point is, if you have, let's have a product state, right, of all spins up, right,
Yeah.
and now you dress it a little bit, and you obtain some ground state of weakly interacting spins, right? That's a very natural operation. Right, so you would like, I think everybody would say, okay, this dressed state is not really different from the original state, right? Okay, it's a dressed version, it's not the same state in Hilbert space or on the algebra, but it's clearly equivalent. It's a bit the same. So, and you don't even need renormalization group to sort of express that it is the same, right? But its entanglement entropy is not the same, right? The product has entanglement entropy 0, and if you just perturb a little bit away from the product, you will have a non-zero entanglement entropy. So I think it's just not the right notion.
Yeah.
And you could sort of, there are other notions which sort of have more chance, like there is something like topological entanglement entropy of which people think that it characterizes and classifies intrinsic topological states, so states that I actually did not talk about, but states with anyons. But that's already a more, that's already a much harder, or not harder, but it's a more intricate object. It's not just the entanglement entropy of a region with respect to the rest. You've perhaps seen the drawings. You need then a partition into 3 regions and so on. And okay. That's perhaps not what you are asking.
Okay. Are there any further questions?
Was crystal clear, I guess. So no questions.
Yeah. Well, okay. I don't see any.
Okay.
Thank you again, Wojciech, for your
Okay,
talk.
Manfred. It was yeah, nice to be there. And please, Jochen,